All right, everyone. Welcome to the second talk of the day. So it's my great pleasure to introduce the speaker, Fahad Panolan from IIT Hyderabad. So prior to joining IIT Hyderabad, Fahad he completed his PhD from IMSC in Chennai, and he was a postdoc at the University of Bergen. So Fahad has a very rich track record of exciting advances in parameterized complexity, especially in the context of matroid-based techniques and also in the theory of geometric graphs. But in the current context, more recently, he's published some exciting work in this recently popular line of research called hybrid parameterizations. So in this work, roughly the objective is to take advantage of all the hard work that people have done in the last 3 decades in the area of parameterized complexity. And the goal is to develop new parameterizations that simultaneously generalize all of these well-studied parameterizations, and B, obtain novel fixed parameter or approximation algorithms that exploit these parameterizations. So this sub-area has taken off in the recent past with several papers at high-profile venues like Foxora, etc. And over the course of 2 talks, Fahad will tell us about some of his recent work in this topic, one today and one tomorrow. So Fahad, whenever you're ready, the floor is all yours.
Okay. Thanks, MSR, for the introduction. So these 2 talks are, based on 2 papers or 2 papers, and which is listed here: FPT algorithm for elimination distance to bounded degree graphs, and deletion and elimination and decomposition to hereditary graph classes are equivalent. And thanks to the co-authors of these papers, and they are here, like Adancha Agrawal, Lokin Kanesh, and Daniel, MSR, Saket, and Merav. I think Saket and MSR are here. And so today, first we will see some definitions, and if time permits, we will see a proof sketch from the first paper, and tomorrow we will see a proof sketch from the second one. Okay. And feel free to interrupt at any point in time if you didn't understand some concept. So first, what is a hereditary graph class? A class of graphs is called hereditary if for any graph G in that class, all its induced subgraphs are also belongs to H. And the examples of hereditary graph classes, you can see many of them. Say, for example, edgeless graphs, graphs of maximum degree at most D, triangle-free graphs, forest, bipartite graphs, planar graphs, caudal graphs, and many more. Okay, so for all of these graph classes, you take induced subgraphs, they will have the same property. Okay, now I want to define about some special hereditary graph classes. Okay. Okay. Now, some special graph classes. Okay. So, given a finite set of graphs, an F-free graphs is a class of graphs with the following property. Okay. For any graph in F, all its induced subgraphs also belongs to F. Okay. So, look at our examples which we have seen. Like one of them is edgeless graphs. So this is, has a finite forbidden set of induced subgraphs where that F contain only one graph, which is K2. And if you look at the graphs with maximum degree at most D, then F will be like all graphs on D plus 2 vertices with max degree D plus 1. So this graph class is F-free for this particular F. And for triangle-free graphs, F is just a K3 containing one graph. And for these graph classes, forest, bipartite graph, planar graphs, and caudal graphs, we don't have a finite forbidden induced subgraph characterization, because to get for forest, we should not have all cycles, so that will be infinite in number. For bipartite graph, we don't want all odd cycles, again that is infinite in number. And you can think about the other two, like it will also require infinite number of forbidden subgraphs, forbidden graphs in F. So this is the definition of F-free graphs. Okay. Now I want to talk about F minor free graphs and F topological minor free graphs. Okay. So first I will recall the definition of minors. A graph H is a minor of G if H can be obtained from a subgraph of G by edge contractions. For example, I want to say that H is a subgraph minor of G. So you delete this red edge and this vertex and the endpoint, one of the endpoint of this one, and you just contract the green edges, and what you will get is H. So from a subgraph, by doing edge contraction, you are going to if you are going to reach H, then H is a minor of G. Okay. Or formally, like you can say that like there exist connected sets. They are vertex disjoint, which is circled here, and the edges of that each of these connected sets, if you contract, and then this H will be a subgraph of that graph, then H is a minor. Okay, so that is another definition. And this kind of like this is called like this function, like connected sets, and with these properties, this is called a minor model. So you should be able to get connected sets, like one for each vertex here, and then the edges you contract. Okay, so there should be one more here, which is singleton. Okay, contract the edges in the connected sets, and then what you eventually get is a graph similar to H or isomorphic to H, after from a subgraph. And now I will define something called a topological minor. Topological minor, a graph H is a topological minor of G if H is obtained from a subgraph of G by special edge contraction. We don't allow all types of edge contraction, but some special edge contraction. What is this speciality of this edge contraction? At least one of the endpoint, endpoint of the edge you are contracting should have degree exactly 2. Okay, then only you will be able to contract it. Okay, so for example, in this one, if you just delete these red edges and then these two red edges, and then if you notice these for these green edges, at least one of the degree is 2, and you can contract it. This green edge you can contract it. For the other two green edges also, one of the endpoint has degree 2, you can contract it, and what you will get here other than this vertex will be isomorphic to H. Okay, so in that case you call H is a topological minor of G. Okay, or in other words, what you can think about is like take a subdivision of H. By subdivision I mean you can place many vertices on the edges of this edge, like as you like, and that should be isomorphic to a subgraph in G. Then like that is another way of looking at it, and then you can say that H is a topological minor of G. Okay, now I want to talk about a graph class which is called F minor free. Given a finite set of graphs F minor free graph is the class of graphs which has the following property: G in pi if and only if G does not contain any graph from F as a minor. Okay, so any graph from F is forbidden as a minor in G. Okay, so such graph classes are called F minor free graph classes. Okay. And the class of F minor free graphs is minor closed, which means that if G belonging to this class pi, which is like F minor free, then any minor of G is also belonging to the class pi. Okay, because if in a minor you are able to see a forbidden structure from F, then in G also you will be able to see it. Okay, because of that, F minor free graphs are closed under taking minors. Okay, and in fact the converse is also true. If pi prime is a minor closed family of graphs, which means that I have a family of graphs which is minor closed. The meaning is for any graph G in pi prime, all its minors also in pi prime, then pi prime is F minor free for some finite set of graphs F. And this follows from the graph minor theorem, which says that undirected graphs, like all the graphs we consider here are simple undirected graphs, and which is well quasi-ordered by minor relations. Okay, if you didn't see this result, fair enough. You only need to know that, the converse is also true. If a graph class is minor closed, then it is F minor free for some finite set F. Okay. Okay, now take our examples. Now edgeless graphs, and this is F minor free for F containing one graph, which is K2, an edge. Okay.
Fahad, there's a question in the chat asking if you could briefly summarize what well quasi-ordering.
Can you define? Okay, so the definition of well quasi-orderedness is that look at the partial order of the graphs under the minor relation. So H is related to G if H is a minor of G. Then in this partial order, there will not be any infinite anti-chain. So infinite set of graphs which are not at all related, any one of them. Okay. So that is the one line, that is the definition of it. Okay. So as I said, for these two talks, we don't need to know about well quasi-ordered like that definition, but you need to know that the converse of like what I said before is also true. Any minor closed family is also F minor free for a finite set. And that comes from, this result. Okay, so for edgeless graphs, it is F free where F is just one graph, which is K2, an edge on two vertices, that is K2. Okay. For planar graph, it is minor free where like F is K5 and K33, like Wagner's theorem. And for forest, F is, K3, just a triangle. And these graph classes are not F minor free, okay? Because look at triangle free graphs, the second one. If you take a C4, which is triangle free, when you contract an edge, then what you're going to get is a triangle. And you know that F minor free graphs are minor closed, so triangle free graphs are not minor closed. And similarly, from a bipartite graph, by contracting, you should be able to get a non-bipartite graph. For example, you take an odd cycle, take an even cycle, contract, you will get an odd cycle. For chordal graphs, any graph is a subgraph of a clique. A clique is a chordal graph. So this is also not minor closed. And what about graphs of maximum degree at most D? This is also not minor closed, because if you take these two vertices with the degree D, say D is say 5 or 6, okay, and then if you contract the middle edge, what you're going to get is degree more than D. So by contracting an edge, you will reach to a graph which has degree more than D, and hence it is not minor closed. Since it is not minor closed, there is no finite set F such that it is F minor free. Okay. So now let's move on to F topological minor free graphs. Okay. Now, how do we define F topological minor free graphs? Oh, it should be F topological minor free. There is a typo here. Okay, is a class of graphs pi, G in pi, if G does not contain any graph from F as a topological minor. Okay. Now, the class F topological minor free graphs is topological minor closed in the sense that you pick a graph in it and take a topological minor of a graph in that class. It should also be in that class, because if you're able to find something for a topological minor, you should be able to find it in the original graph. But it is not minor closed, and the reason is the figure we have seen. By just contracting an edge, okay, like the reason is like the graphs of degree max degree D is F topological minor free, where F contain only one graph, which is one vertex K1 D plus 1. Okay. And if we don't have K1 D plus 1 as a topological minor, then that graph will have degree at most D. Okay. And so the class of graphs which has max degree at most D is F topological minor free, where F contain, K1 D plus 1. Okay. And that is not a minor closed family we have seen in the last slide. So you can have a graph where when you contract edge, what you're going to get is a graph with degree more than D. Okay. Now, okay. The set of undirected graph is not well quasi-ordered by the topological minor relation. Because of that, we can't say the converse is like for the case of F minor free graphs, we said, if a graph class is minor closed, then there is a finite forbidden minor characterization. But such statements are not true for topological minor free graphs. So like if we have a class of graph which is closed under closed under taking topological minors, then we may not be able to get a finite set of graphs such that that graph class is F topological minor free. Okay, so that is not possible to get. Indeed, there exist graph classes for which this is not true, and that can be constructed from the fact that this is not well quasi-ordered. Okay, so the only thing you need to know here is like the converse of what is this one. The first statement is not true. Okay. Now, the first set of graph classes, can we write it as a F topological minor free graphs for some finite F. For edgeless graphs, I think I don't know how to remove this one. Let me erase it. Okay, no, I don't know. Okay, so for edgeless graphs, this F is K2. So edgeless graph is F topological minor free, where F contain only one graph, which is K2. And for planar graph, it is K5, K33. And for graphs of max degree at most D, it is F topological minor free, where F is K1 D plus 1. And note that this graph class is not F minor free for some F, for a finite F. And for forest, again K3. But these graph classes, say triangle free, bipartite graph, chordal graph, they are not F topological minor free. Okay, so you can, like whatever I have said before, you just take a C4, by contracting, you will get a triangle. Okay. Similarly, take an even cycle, contract, you will get an odd cycle. And because of that, these graph classes are not F topological minor free. Okay, so these three, right? This will not come under, F F free, F minor free, F topological minor free. And the rest of the graph classes which we have discussed here come under any one of these. Okay, where the graphs of max degree come under F topological minor free and F free, but not F minor free. Okay, so now I want to emphasize one more point here. If pi is F minor free, then pi is also F prime topological minor free for some finite set F prime. So which means that if some graph class is F minor free, then it is also F prime topological minor free for some finite set F prime. So that graph class is even more general one compared with F minor free. Okay, now coming into so this is what I want to talk about graph classes. Now we will define some problems, and where like vertex deletion and vertex elimination problems, and then we will state some result, and hopefully we will give some proof sketch of some of the result. Okay, so so a vertex deletion problem looks like this. So we have a graph class H, and we are given a graph G and an integer K. The question is, can we delete at most K vertices such that G minus S belongs to this graph class H? Okay. And if you take H different graph classes, like say if you take H to be edgeless graphs, then that problem is vertex cover. Can you delete K vertices to get an edgeless graph which is vertex cover? Okay, and if H is forest, then that is feedback vertex set. Like after deleting K vertices, you want a forest. If H is bipartite graph, this is odd cycle transversal. And if H is planar graph, the problem is called planar vertex deletion. And if H is chordal graphs, then the problem is called chordal vertex deletion. All these problems are fixed parameter tractable. Like there are lots of algorithm for all these problems, and there are lots of technique developed while designing good algorithms for these problems. What is the meaning of fixed parameter tractable? Like and when parameterized by K, where K is the set of vertices which you want to delete, the set of the cardinality of the deletion set. The problems can be solved in time f of K and polynomial in N, where N is the input length. So you can think the number of vertices, and K is this number, and F can be any function. Okay, but it should be polynomial in N. So this running time should be small when K is small. Now we can ask more general question, right? So H is a F free graph or F minor free graph class or F topological minor free graph. So we are given some F, and we want to get into this F free or F minor free or F topological minor free graphs after deleting K vertices. Okay, so F deletion, that problem, like after deleting K vertices, I want the graph to be F free. That problem is called F deletion problem. And for that, there is a simple branching algorithm which runs in time, FPT time, and one of them, that algorithm we will see, because I want to introduce branching algorithms. And for F minor deletion, and it follows from the graph minor theorem projects of Robertson and Sumer, that F minor deletion is FPT. In the sense, F minor deletion, all the graphs which are S instances of F minor deletion for any fixed K will be a minor closed family. And because of that, we just need to check whether the graph G contain finite set of minors. If it contain any of those finite set of minors, then it is no, otherwise yes. And minor testing can be done in polynomial time. Okay, where the pattern graph has constant size, okay? Or n cube time. Okay, order n cube time, and that comes from this work. And F topological minor deletion, after deleting k vertices, I want to get into the graph class, which is F topological minor free. And for this also, there is also an FPT algorithm, which is very recent, like in 2020. Okay. And all these problems are fixed, like as I said, fixed parameter tractable. Okay. Now I will explain a very simple algorithm for F deletion. Like I want to delete k vertices, get into the F free graph. So the algorithm goes like this. So you can think that, you know, the vertices, sorry, the graphs in F, they are constant size. Okay. And you want to delete k vertices to get into the F free graph class. So if G contains an F free, if G is F free, then you don't need to delete anything. If k equal to 0 and G is not F free, then it is a no instance. And otherwise, you just find a graph, a subgraph, an induced subgraph H of G, which is isomorphic to F. And then you know that one of the vertices from H need to be in the solution. So you recursively solve G minus V, K minus 1 for all V in H, and the output yes if and only if at least one of the recursive call returns yes. Okay. This leads to an algorithm, like the recurrence tree looks like this, like you started with the G comma K and you picked a forbidden structure, which is H. You don't want that because you need to hit any of these vertices from it. So you just trying to recursively solve it. And so essentially we are saying you branch on H, and H has, you know, a constant size. And then the depth of this recursion tree will be at most k, because when k equal to 0, that will be your base case. And the number of branches, number of children for every node here will be the max size of a graph in F. Suppose it is D, then it will, the number of nodes in this tree will be D plus, you know, D to the power k plus 1. Okay. And that leads to an FPT algorithm. So it will have running time D to the k plus 1, where here D is a constant, and for each node you are spending constant time, polynomial time, because you just need to find an induced subgraph of constant size, which is isomorphic to a graph in F. Okay. So our algorithm, like which we see for the elimination, which I'm going yet to be defined, is a branching algorithm. So our algorithm will be of this nature. Okay. Now, suppose, you have seen an algorithm for F deletion problem. So you want to delete k vertices to get into F free graph. Okay. Now, look at the following scenario. Suppose you have a graph which contains lots of connected components. Then the cardinality of deletion set could be large, because you need to add up the deletion set from each of the components. Okay. So the better choice for the parameter is the maximum cardinality of a deletion set for a component, right? Because like for each of them separately, you could try to solve, and with the parameter being smaller than the deletion set size. Okay. And look at another scenario where, like, you have a cut vertex, and which will make the graph into many connected components. And if you pick this cut vertex, then you will get lots of connected components. And then you could probably solve in each of, like, it's better to solve in each of these connected components with a smaller parameter. And then here also the better choice for parameter could be like 1 plus maximum cardinality of a deletion set for each component. Okay. And this, intuition leads to the definition of something called elimination distance. So I will formally define what is elimination distance in the next slide. Okay. An elimination distance to F free graphs, okay, which is 0 if G is F free. Otherwise, you take, it will be like if G is connected, then you think about your cut vertex scenario, which is 1 plus minimum of elimination distance of G minus V, where V belonging to V of G. Okay. And if G is not connected and it is not F-free, then the elimination distance is maximum of the elimination distance of H. Okay. So essentially, like if there are connected component, you find elimination distance in each of these component and the maximum is yours. And if it is connected and not F-free, then the minimum over all the vertices, you pick one vertex and then that you take into solution, like delete, and for the remaining you try to find out the elimination distance. So it is, recursively defined. And this elimination distance you can define to any graph class. Okay, how to get rid of this? Okay, any graph class, for example, right? Like elimination distance to H, like instead of F-free, you just make it here, whether G belonging to H or not. Okay. So elimination distance to a graph class is recursively defined like this. Okay. Now pictorially you can see it as follows, and this is introduced by Bulian and Dawar in 2016. Okay. Pictorially it looks like this. Okay. There's a forest. Okay, and that is what on the top. And in this forest, these nodes, the nodes of this forest are vertices from my graph G. And after delete the vertices in this forest, X, there will be lots of connected component. And for each connected component, it sees only neighbors from a leaf to root path. Okay, the forest is a rooted forest. Okay, so for each connected component, after I delete X, should see neighbors only from a leaf to root path. Okay. And if you look into any edge in the graph, either it is in a component or it is from a component and to this forest, and which of course will satisfy the property I mentioned before. And it could be that if two vertices are in that forest, then it should follow an ancestor-descendant relationship. Okay, and this is the same as what I defined in the previous slide. Pictorially, it looks like this. So, like you delete one and then find spread here. Any questions?
Fahad, in this picture, did you have a specific edge in mind?
Okay. In this picture, I don't have any specific H in mind. And the property is after I delete X, this G minus X should be in H.
Right. Okay. And this is probably a silly question, but what is the difference between this distance that you have defined and the vertex deletion distance?
Okay. In the vertex deletion, okay. Now, what is the distance I defined here? The distance will be the depth of this rooted forest. Okay.
Right.
And in the vertex deletion, it is cardinality of the deletion set. Okay.
Right. Okay.
And the elimination distance is always less than or equal to
Correct.
deletion, vertex deletion, because the vertex deletion you can put it on a path.
Correct. Makes sense. Yeah. Thanks.
And few things to note: G minus X belonging to the graph class you want, and for each connected component, it see neighbors only from a leaf to root path, and for any other edges which is between two vertices in X, they should form an ancestor-descendant relationship. So these are the properties. And the measure or the elimination distance is defined to be the depth of this rooted forest. Okay, so that is what is time? Okay, so that is about the elimination distance. Now, when H is the graph which is the empty graph, which means that what you need, then the elimination distance to H, okay, this H should be a subscript here, there is a typo. Elimination distance of a graph to H, where H is the empty graph, which means that at the bottom I don't have anything, is the tree depth of G. Okay, what is the meaning? Like we should be able to get a forest of a rooted forest of depth, tree depth of G, and there will be a bijection from the nodes of the tree to the graph, the vertex set of the graph, and for any edge in the graph, the corresponding vertices in the tree will be in the ancestor-descendant relationship. Okay, so this notion, elimination distance to H, generalizes the notion of tree depth. When H is equal to 1, the graph class containing one empty graph, then elimination distance is same as tree depth. Okay, so it generalizes the notion of tree depth. Now we can ask the following question. Now I already mentioned that elimination distance is smaller than the deletion set size. So we can ask this algorithmic question, given a graph G and an integer K, whether the elimination distance of that graph to the class H is at most K. Okay, like the vertex deletion to H. And now take out these three graph classes, which is F free for a finite set F, F minor free for a finite set F, and F topological minor free. And this will not, subsume, this caudal or bipartite, graph classes, but just focus on these three general problems. Okay, these three general problems will cover a lot of graph classes. Okay, F free graphs, F minor free graphs, F topological minor free graphs. Okay, when H is this one, we can prove that that problem is FPT. That means that like deletion to and elimination to F free graph is FPT when parameterized by K, where K is the elimination distance, not the set of vertices, not the cardinality of set of vertices you delete, but it is the depth of that tree, elimination forest, whatever we call it. Okay, and Bulian and Dawar proved that when H is F minor free, the problem is FPT. And here they asked the following question: if H is the set of graphs whose max degree at most D is, then is the problem FPT. Okay, and that is a special case when H is equal to F free. Okay, and that is also a special case when H is F topological minor free for K1 D plus 1. Okay, so for that graph class, which is not F minor free, can we prove that elimination distance to H, which is graphs of max degree at most D, where D is a constant, is FPT? And we answered that question, and that is the first bullet point. Okay, when H is F minor F free, then we can prove that it is FPT, and we will see a proof sketch today. Okay, and then we can and we can prove that, like in the other work, we proved that when H is F topological minor free, still it is FPT. Indeed, we prove even more general result, which subsumes all the other graph classes, which is not any of these F free, F minor free, and F topological minor free, which we have seen before, like caudal graphs, bipartite graphs. For those cases also, we can get that elimination distance to that particular class is FPT. Indeed, we prove that they are elimination distance to H and vertex deletion to H are FPT equivalent, which means that if one is given as a black box, we can prove the other. Okay, and if H satisfies some mild conditions. Okay, and that I will explain in the tomorrow's talk. Okay, so today we will focus on this one. Okay, the first bullet point. When H is F free, where F is a minor, F is a finite set, and then the question is elimination distance to H, okay, or F free graphs, then that is FPT, and that will be a branching algorithm. But before, we need to go through some theorems or some result before getting into that branching algorithm. Okay. Now, one of the difficulty. Is there an eraser?
Are you using preview?
No, yeah, I think it's preview.
Neil, do you happen to have any answer to this?
Okay, I will find out later. Let it be here. Okay, it's good that I used yellow. Okay. Now, one of the difficulty in this problem is the set of vertices in the elimination forest, which I delete, could be very large, but its depth is k. Okay, depth k, but a huge number of vertices in the deletion set. Then, if that is very large, then we cannot do a branching algorithm where we keep deleting, keep decreasing number of vertices in the elimination forest, because that elimination forest is so large. Okay. Now, just try to look at the case when elimination forest is very large. Okay, and then see some structure. Okay, and then try to utilize that structure. Okay. So, suppose the elimination tree, which has bounded depth, okay, but it contains lots of vertices. Then you will be able to find out a leaf to root path in that. Like for the time being, assume that this elimination forest is a tree. Okay, and whatever I am going to say will extend to forest as well. Okay, suppose this elimination tree contain lots of vertices but a depth k. Then you will be able to find a leaf to root path that is a separator separating lots of vertices. In the sense, like you will be able to find out a root to leaf path, and all the vertices to the left of it in this figure, that is also a large number. And then the number of vertices to the right of this, this leaf to root path, that will also be very large, which means that in my hypothetical solution, I have an elimination forest and that contains lots of vertices, then there is a good separation. What do I mean by good separation? A separator of size at most k, and in the left side you will see lots of vertices, and in the right side you see lots of vertices. Okay, where this large depending on how large this tree is. Okay, so the point is, if elimination forests contain lots of vertices, then the graph has this kind of a separator. And now we will use one of the theorem, one of the result by Loxanov et al., which says that if we are able to like certain problems, if you are able to solve on graphs that does not contain these kinds of separators, like a small separator separating lots of vertices, then there is also an algorithm on general graphs. So I will formulate it in the next few slides. So that will allows us to completely ignore this case. Completely ignore this case means, in my hypothetical solution, the elimination forest will not contain lots of vertices, because we only need to solve the problem when the graph does not have these kinds of separators. Okay, so I will explain it in the next slides. Okay, for that I need to define something called SC unbreakable graphs. What is an SC unbreakable graph? A graph for which this kind of separator is not present. What is this kind of separator? A separator of size at most C, such that in the left side you have more than S vertices, and in the right side you have more than S vertices. This kind of separator, if this kind of separator is not there in your graph, then that graph is called SC unbreakable graphs. Okay. Then the theorem says the following. Okay. Okay. Now, so here I will be a bit vague. Suppose here CMSO means counting monadic second order logic. Suppose we have a formula phi, which is in the which is a CMSO formula. So assume that some here those who didn't see CMSO, just assume that some graph properties with some a graph properties with some specific kind of graph properties. Okay, and then suppose for all C there is an S such that they independent of this C and S, and for testing whether H satisfies this formula phi. Okay, so instead of this formula phi, you think that a graph property. Suppose we have an algorithm for testing whether H satisfies some property, and this property should satisfy some logical conditions. Okay, on SC unbreakable graphs. So here for all C, this S is given by this theorem. Okay, then this result says that then there is an algorithm with running time order n to the d for testing whether G satisfies this property on general graphs. So we just need to come up with an algorithm on SC unbreakable graphs for all C, and this S will be given from this theorem that will depend on C, and this D is independent of S and C, and the constant here depending on the formula size, or in other words the property, graph property, and S as well as C. So you think they are constants, okay, or they are parameters. Okay, so this is that if we are able to some graph problem, if we are able to solve on unbreakable graphs, then there is an algorithm for the problem on general graphs. Okay, now what is the implication of this in our setting? If we prove that elimination distance to F-free graphs is having this property, which is CMSO expressible, and we prove that elimination distance to F-free graphs is FPT on K alpha K unbreakable graphs for all K. So here K is same as this C, and alpha K will be given by this result, and for all K alpha K unbreakable graphs, if you are able to design an algorithm for elimination distance to F-free graphs and prove that this problem is CMSO expressible, then elimination distance to F-free graphs is FPT parameterized by K on general graphs. Okay, is this implication clear to you? Any questions? So next I will explain how to next I will explain this problem. Elimination distance to F-free graphs has a certain characterization. So I will give that characterization, and those who have seen CMSO will be able to get that this characterization is CMSO expressible. Others can go and read and then understand that this characterization will help you to come up with a CMSO expressible formula. Okay, so in the next few slides I'm going to explain that elimination distance to F-free graphs has some characterization, and that some interesting characterization. Okay, and that will help us to prove that it is CMSO expressible. Okay, and then later, probably tomorrow, we will explain that elimination distance to F-free graphs is FPT on unbreakable graphs, and that will prove that it is FPT on general graphs. Okay. Now fix any k, okay, an integer k, and look at the graph class of graph such that G comma k is an S instance of this problem. Okay, so this is a graph class. Okay, and we want to prove that it is, in CMSO expressible. Instead of that, I will give you a characterization of, this graph class. Okay. Now, suppose G belonging to QF, which means that G comma K is a S instance of this problem, which means that there is an elimination forest, and after you delete that elimination forest, what you get this graph, which is F-free, and for each connected component, their neighbors are from a leaf to root path, and all the remaining edges will be the endpoints of the remaining edges of G will form an ancestor-descendant relationship. Okay. Now, just a minute. Okay. So one of the property we have is G minus X after deleting all the vertices in the elimination forest is F-free. Okay. And other thing I will say that torso of X, which I will define in a minute, has tree depth at most k. What is torso of X? X is the set of vertices here. Okay. And the torso of X is a graph on vertex at X, and the edges will be defined as follows. You pick any two vertices in X, you add an edge between them. If there is a path between them in G, whose internal vertices are outside X. Okay. So you pick any two vertices in X and add an edge between them. If there is a path between those two vertices, where the internal vertices should come from the bottom, it is from outside X. Okay. Now, then what you will get? You will get, like, look at this figure. Okay. By the property of this elimination distance, the edges you are going to add will have those endpoints will have ancestor-descendant relationship, because if you have a path which is fully outside, that will be going through a connected component and coming to here. Okay, because for any connected component, you have only neighbors on a leaf to root path. Because of that, torso of X, look at this elimination forest. Those edges of torso of X will form an ancestor-descendant relationship in this tree. That implies that the torso of X, the graph on X with some additional edges, has tree depth at most k. Okay. And in fact, the converse is also true. Suppose I am able to find a vertex at X such that G minus X is F-free and the torso of X has tree depth at most k, then G belonging to this QF, or in other words, G comma K is a S instance of this problem, elimination distance to F-free graphs. Okay. And the proof is, you only need to like from the tree depth of torso of X, you will be able to construct a elimination forest for the problem of depth at most k. Okay. Okay, so what we have proved is G belonging to QF if and only if there exists a vertex subset X such that G minus X is F free and torso of X has tree depth at most K. And now tree depth is a minor closed property. What is the meaning of that? Like suppose tree depth of a graph G is at most say some number Q, then for any minor of G also has tree depth at most Q. And this implies that the set of graphs which has tree depth at most K has a finite forbidden minor characterization. Or in other words, there is a family F prime of finite graphs such that torso of X has tree width at most K if and only if torso of X is F prime minor free, where F prime is a finite set. And this comes from the fact that minor closed families are F prime minor free for a finite set F, for some particular minor finite set F prime. And this gives the following characterization. G belonging to QF if and only if there exists a vertex set X such that G minus X is F free and torso of X is F prime minor free, where this F prime depend on K. And these two properties, F free and F prime minor free for finite sets, this can be expressible in this particular logic that I am not going to explain to you. But using this characterization, one can prove that these two characterizations can be expressed in this particular logic, counting monadic second order logic. Okay, and then which means that this characterization, whether G belonging to QF or not, can be expressed in this particular logic. Okay, and using these two, this characterization. Okay, so what we have proved here is like our problem. Like so, you fix any K, and then look at all the graphs G such that G comma K is a S instance of the problem. Of our problem, then this graph class is CMSO expressible, and this means that we have proved the first one. So elimination distance to F free graphs. So for any K, I have a CMSO formula for that. Okay, so for any K, like for different K, this formula will be different, but if I fix K, I will be able to get a formula which says that which all vertices are belonging to this class or S instances of this problem. So the first part, like I gave you some idea, like some characterization of this problem when I fix K, and that can be used to express this in CMSO expressible. And then because of that, we proved the first part, and then that says that we only need to prove, or we only need to design an algorithm which is on unbreakable graphs. When a graph is unbreakable, the meaning is in my hypothetical solution, the elimination tree or the elimination forest does not contain lots of vertices. The number of vertices in the elimination forest will be bounded by a function of K. Okay, and using that, we will design a branching algorithm to for the second bullet point. That is, when the graph is K alpha K unbreakable, the problem is FPT. And then put together with this result, we will get that even on general graph, this problem is FPT. Okay, so so this requires some time. So I will talk about this tomorrow, and I will also talk about the other result, which is F topological minor when H is F topological minor free. Again, that problem is FPT. And both of them, I will give a proof tomorrow with, and I will also explain some more result in this line of work. With that, I think I will stop here.
Thanks a lot, Fahad, for the nice introduction and proof sketches so far. So are there any questions for Fahad?
So one question, Fahad, is there is non-uniformity at many places, right?
Yes, this will be a non-uniform algorithm.
I mean, I know that unbreakable, if you do it for unbreakable, then it's for general graphs, that is a non-uniform, but are there non-uniformity coming up at other places as well?
For the second bullet point, there is no, that is uniform, but the non-uniformity comes from, for every k, the formula phi is different.
Oh, that's also okay.
And not for the second one. Second one is a branching algorithm. But like for these problems, we could get uniform algorithm via different route.
I see.
So
even for the general problem, is it? You can get uniform.
Yeah, you can get yeah, but for most of the problems, you can get uniform algorithm.
I mean, for most of the problem, meaning for specific classes.
No, F minor, oh, sorry, F3 you can get. Yeah, F3 you can get. Yeah, F3 you can get uniform algorithm.
Yeah, because for F minor, even for deletion distance, you don't have uniform, right?
F topological, okay, let me see.
For the F minor, you just use Robertson-Seymour, right? Deletion distance.
Yeah, yeah. No, there is a uniform algorithm. You can get an algorithm other than that, like using without using this this formula F3 for some different graph. Using irrelevant vertices, you can get that F deletion problem. Sorry, F minor deletion problem. Using irrelevant vertex technique, you can get an algorithm that is uniform.
Ah, okay, okay.
Unlike this unknown F.
Thanks, Fahad. Are there any more questions? If not, let's thank Fahad again. So Fahad, we look forward to your second talk tomorrow. So thanks again for the talk. And thank you all for joining.
Thank you.